one of the questions that I got was, so what's the difference and what are we actually using? I think there was some confusion between C, ARM, Thumb, and Thumb 2, right? And it's kind of important to understand what the difference is between them and what we are actually using. I am sometimes in lectures mixing C and assembly and going back and forth because some things are easier to explain in C, others are easier to explain in assembly. But you really need to understand, first of all, the assembly code, because C code gets translated down into assembly code before it's going to be put into machine code. So it so happens that this morning Energy Micro, which is a microcontroller company, just had a blog post where this figure was posted in. I thought this is perfect. We can use this as a really good explanation. What happens, if you write C code, you usually use a compiler like GCC, right? So what happens is your C code goes into a compiler. The compiler does a lexical analysis, syntax analysis. If you make mistakes, it will tell you where the mistake is. It can't interpret it. Then it does a semantic analysis before it's going to be put into an intermediate code that the GCC uses to then do optimization on. So there's this intermediate code where GCC does optimization on. And then from there, there's a backend. So the backend would be, in our case, the ARM non-EABI part, where it takes its intermediate language, generates target-specific code, and does some low-level optimizations on this. And then outputs assembly code. That's the stuff down here. So GCC generates your assembly code and then uses the assembler to generate from the assembly code machine code, and then it goes into the linker and does the rest of the whole thing. So if you write C code, there really is an equivalent to what you write in C to what you will later on see in assembly. Now, depending on what level of optimization GCC does, this can be almost unrecognizable. Or sometimes it disappears because GCC recognizes that some of your assembly code was not written very well, or it did something that was not useful, and so it just removed it to speed up the process. Now, in embedded system, this can oftentimes be a big problem for you, because sometimes you do things that the optimizer doesn't know or doesn't understand that this is really what you want to do. For example, we just talked before about how can we wait for 1 second, for example, right? Well, so it's very easy. You take a variable, write a number in it, and then just subtract 1, compare to 0, subtract 1, compare to 0, until you have done, for example, 50,000 iterations of it, which at a CPU that runs at 100 megahertz, 2 instructions it takes 2 instructions per cycle, so 50 million cycles would be 1 second. Now, an optimizer would come in and see that you are just waiting there. That's stupid, right? That's not optimal. So it just removes the whole busy loop, and, well, gone is the second of wait time. But if you do the busy loop in assembly, then the optimizer won't remove anything. So what you put in there in assembly will really be there at the end. So if you use inline assembly, it won't be optimized away by the compiler. Yes? Yes, you can do that. So in GCC then, a way of giving it a tip that, hey, this is really what I want to do is you can declare them as volatile. And then GCC will think, okay, you really want to do this subtraction here and I should not start trying to optimize this. So there are ways of doing these kind of things, but sometimes they can be hidden. You can do optimizations, and if there are multiple different levels of code that you have there, and then somewhere you have not a volatile declared, and bam, gone it is, and your code is gone. So then you have to go back into the disassemble code and see what did the optimizer actually do with your C code. Happens more often than you would think. Okay. Now, lecture number 7, part 2. A couple of other announcements. So we just talked about this. Difference between C and assembly. And now on the ARM architecture, we have multiple types of assembly that we can run. There was the ARM assembly, which was the very first assembly. It was all 32-bit instructions. And then ARM came and was like, well, but we sometimes want to be more space efficient. So they came up with Thumb. And Thumb was then only 16-bit instructions. So Thumb was really just a subset of the ARM instruction set, but all encoded in 16 bits. So you were restricted on some of the options, but it was more or less the same thing, but more code efficient. And then they came around and we were like, well, let's make a Thumb 2 where we actually mix and match. Because the problem was your processor was running either in ARM or in Thumb. It could switch between them from function call to function call, but you couldn't have like a block of 16-bit and 32-bit mixes. So you had to either be thumb or ARM. And now they made thumb 2, where we mix both of it. Now you can have some of the instructions get encoded as 32 bits, others as 16-bit. And that's thumb 2. In the case of the Cortex M3, you can only run in thumb 2. You cannot switch into ARM mode. If you try to do that, it will give you a hard fault and your processor will stop. Yes?
So I finally found the Cortex M3 guide. ARM's site. But it's the Cortex M3, does it do kind of like a hybrid between 1 and 2 and not do some of the 32s? Because you look at that 180-page guide.
Yes.
It goes over the instruction set. It doesn't include everything that's on the full thumb 2.
It all yes. So it is also a subset, and it does not implement all of the different functions. So for example, there is in thumb 2, if I'm not wrong, there is a diff, and the Cortex M3 does not have a divider. Now the Cortex M4 has a divider. So some functions won't work, others will. What will happen is if you tell the assembler to assemble something for a specific architecture, so Cortex M3, and if you use assembly functions that don't exist on that architecture, it will throw you an error telling you that this does not exist on the architecture itself. Yes?
Why the ARM system is thumb 2 that can run the instructions?
Legacy. It's just there. And yeah, the A series and like the A9, A10, and so on, they all support ARM and thumb. And you have libraries that were compiled and written in ARM, and they're there, and you can use them and run them. Yes?
So thumb 2, are these just a subset of ARM instructions, or they're like kind of optimized instructions?
So if you actually go onto the Wikipedia page, there's a little bit of more explained history of what's actually going on with this whole thing. And with thumb 2, they really wanted to get the benefit of 16-bit instructions with the flexibility of 32-bit opcodes. So you have more variety, but still be space efficient. And with thumb 2, they actually got there by making it optimal with respect to size, but also speed. So it's kind of a mix. Yes, thumb 2 is probably better than ARM itself, if you have the sources and can recompile them. They also made a unified assembly language, the UAL, which is a unified language. You can write it and then just say, I want this compiled into ARM assembly code, or ARM opcodes, or I want to compile it into thumb opcodes. So that's the UAL language that you all use. And then you just tell the assembler what it should generate. Any questions? So we are all, most of the time, using thumb 2 in this class. Okay. And then starting lab 5, I think, is it when we will switch over to C, and we will only look at the assembly if we have to do special instructions that are not equivalent in C, or if you really want to know what's going on. Yes?
So it seems like thumb 2 has everything that thumb 1 has, just more.
Yes.
So if you just use stuff in thumb 1, you won't be like, well, you're not using the special thumb 2 instructions. Minus 10 points.
No.
So I can use the much easier to read thumb 1 reference card than the slightly more complicated thumb 2 reference card.
It's the one that I gave you in the class. Which one is that?
That's a thumb 2.
Then it's the thumb 2 one. That's the one that you will be allowed on the midterm.
So I have to learn the stupid operand 2
Yes.
mess?
Yes. But you don't have to use it.
Okay.
It's oftentimes optional.
Some of the shift instructions.
The assembly will be easy that you have to write in the midterm. So it shouldn't be complex. It should be something that you have seen. It will be adds, loads, stores, branches. That's the kind of stuff you should know. Not the super exotic who knows what. Maybe like one of the multiply and accumulate will help you. But yeah. Okay. Another question that was very important, I think, is who clears interrupts, software or hardware, and how can I find out? And that's really the problem. You don't really know. Like, it really depends on the peripheral and who implemented that particular peripheral. Oftentimes, you have to clear them in software, but not always. So how can you find out? Well, you read the datasheet. Because the datasheet will tell you what you have to do, how to program the peripheral, how to use the peripheral, which register to set up in order to get the interrupts out, and also to clear the interrupts themselves. Here's an example. If we go into the data sheet, this is the MSS user guide, we find this big table for, in this case, the timer register map. Right? So there's a timer in there. This is the register map for this timer. This will tell you which register sits at what memory location, what type it is, read or write, and what the reset value is, plus a little explanation back here. So if you want to find out what's going on with the interrupts, well, we probably should look at the control register, right? Because that's the timer 1 control register that will set up something controlling the timer. And if you look through this list, we find this guy here, the MIS, which is the timer 1 masked interrupt status, and RIS, timer 1 raw interrupt status. So maybe we should also look at these two. At the same time, if we look at this MIS here, we see that this is a read-only register. So probably not the one where we can go and clear the interrupt. So let's look at this one here, which is a read-write one. First, control register. This is a very typical control register definition that you get in the data sheet. You have bits 31 through 3. It tells you there will be 0, but it's not guaranteed. So as software developers, just ignore what's up there. It should be 0, but who knows exactly. Then we have bit number 2, which is the time intent read-write. So interrupt enable. Perfect. That's what we need to write in order to enable the interrupt from our timer. What we have to do is we have to write 1 into this bit of this register, which sits at this location. Right? That's where we write 1 into. That will enable the interrupt. Or if you want to disable it, you write a 0 in there. Timer mode, nothing to do with interrupts. Really, it tells you how the timer counts up or down or resets and stuff like that. We will talk about that later. And then timer enable, it just enable or disable the timer. So it starts counting or stops counting. Okay, so let's look at the next one. So far we could enable the interrupt. Now we have this RIS interface. All the bits 31 through 1 are reserved. Please don't use them. We don't exactly know what's happening. Most likely 0, but not entirely sure. And then we have the RIS itself. And what's here? So we have timer X raw interrupt status. If it's a 0, the timer X has not reached 0, so the interrupt has not happened for this timer yet. If it's 1, timer X has reached 0 at least once since this bit was last cleared. So the interrupt has been 1, the interrupt is set of this particular peripheral. And then we can read, writing a 1 to this bit clears the bit and the interrupt. Writing a 0 has no effect. So if you want to clear your interrupt, what you do is you write a 1 into this bit, and then the interrupt line will go down until the next time the interrupt occurs again. So in this case, software has to clear the interrupt. But there are peripherals out there where the interrupt just gets generated, and then the peripheral doesn't care about it anymore, and then you don't have to go and clear it. All you have to clear is the status bit in the NVIC. Any questions so far? So is it clear with what the NVIC's purpose is, what the peripheral's purpose is in interrupts? Who generates what and how they're handled? Yes?
Can't it just do this on loop? Wouldn't that just be so much?
Do it what?
Loop.
Hmm? What loop?
Never mind.
Okay. Finicky.
I fail.
Minute quiz. Okay. Heads, we take the minute quiz. Tails, no minute quiz. That's an easy one. So what is the first interrupt that gets fired on a Cortex M3?
Reset.
Yes, reset. Right? The system, when it boots up, it first reads the stack pointer and then goes and fetches the reset vector handler from address 4. So it's executing the reset interrupt. Okay. This was another one of the questions, and I think a lot of people got confused, and let's start with a little bit recap and then keep going from where we were last time. What's going on with this whole priority group, subgroup, and how does this really all work? What we can have is different priorities for different interrupts. And every interrupt can be configured for its own particular priority. Okay? And then within this priority, you can have the group and you can have the sub-priority itself. So how does it work? Well, we have 3 interrupts up here that have priority -3, -2, -1. So that's the reset vector, NMI, and hard fault. Reset vector has -3 because you cannot, like there's nothing higher than this. You cannot stop the system from resetting. NMI stands for non-maskable interrupt. It's another one of these interrupts that you can't turn it off. If that interrupt happens, it will execute the NMI interrupt handler. And then we have the hard fault at the priority -1, and there is a special way of turning off hard faults, but usually you don't want to turn off hard faults because it means something went really, really wrong in your system. The rest are programmable from priority 0 down to 255. We have the bit field that sets, okay, where is the partition between preemption and sub-priority, or the group priority and the sub-priority. This is set in a register in the NVIC. There is a 3-bit or 4-bit number where you say how many bits of this 8-bit register is sub-priority, how many are preemption priority. It turns out that a vendor does not have to implement all priority levels because that generates a lot of logic in the background. So oftentimes they opt for only fewer bits. Then what happens is that the lower bits, they're just static zeros, and it's only the upper bits that get used for the different priorities. So in this case, we have 5 bits in the top and 3 bits at the bottom. These 3 bits will never be changed, and these we can use for programmability. Okay? Now, what happens? Let's assume we have 2 different priorities. I didn't put all of them in here. No, actually, these are all of the possible priorities given this bit mask. If you notice here, we are always incrementing by 8, right? So these 3 bits will always be 0. So we have priority 0, 8, when bit 3 is 1. Next, we defined the top 2 bits as the priority group, and then the next 3 bits as the sub-priority. So we get a total of 4 different priority groups, and then the rest 3 bits will define what sub-priority are belonging to the same group. Okay? And we can continue on. So for the last one, 0, C0, that would be the different sub-priorities. Now what happens is that interrupts that are in the same group cannot preempt each other. Only interrupts from a higher group can preempt interrupts from a lower priority. So everybody who is in this group, so any priority like this, they will not be able to preempt each other. They can only be preempted by interrupts that are either in this group, or that group. Yes?
Does sub-priority only matter when there are many interrupts from the same priority group?
Yes. So instead of preempting each other, when there are multiple interrupts pending, they will go through this order, depending on the different priority, in case they will be handled, so one after the other. And we'll look at that in a second on how tail chaining and other stuff is happening. Yes?
It says that we have in group 5. In group 5, we have another table last session that says that print priority field is bit 6 and 7.
Yes, 6 and 7. So group is set to 5, which means the last 5. So basically, bits 0 to 5 are the sub-priority bits.
Yeah, but here we have 3 until 7 as sub.
No. Sub-priority starts here down to 0. These are not implemented. They will always be 0. Right? So you can only have this either at this bit. This is the first one that you can have as sub-priority.
So here we can have 64 sub-priority, but only have 6. Okay.
It depends on where you want to go with this one here. Right now we have 4 priority groups, and we have 8 sub-priorities per priority group. So which would be 32, if I'm not mistaken. So there are only up to 32 levels. of priorities.
Now, how many sub-priority for every?
In this one here, in this particular case, we have 8 sub-priorities per priority group because of how this was set up.
But the maximum is 64. Because we have 6 bits.
32.
The sub-priority field is 0 until 5.
Yeah, but bit 0, 1, and 2 are not implemented. Come after lecture, I can explain it better. Yes?
So each interrupt will have a preempt level and a sub-priority level?
Well, what happens is you set it to a priority. Right? You set it, for example, to 38. And by having priority 38, it will belong to priority group 0. If the group bit was set to 5. Let's assume that the group bit was set to 4, okay? What would now be the different groups? How many groups would we have?
6.
We went 1 down with this one here. So we went, the sub-priority is now 4. The groups is the preemption groups, sorry. So, oh, the groups is, that's a level, it's like a, I think it's a 4-bit number or a 3-bit number in a register somewhere in the NVIC, where you just tell how many groups you have. So how many bits of the priority you will use for sub-priority and for preemption priority. So in this case, if it's set to 5, it means that everything from bit 0 to 5 is used for sub-priority, and 6 and 7 is for the preemption priority, or the group. Okay? So if we set it to 4, what will happen? Sorry? Exactly. We now have 8 groups and 4 sub-priorities per group. So if the priority of your device was set to 38, you will now belong to group 0x20. And now all of a sudden, like before they could not preempt each other, but now all of a sudden interrupt 0, priority 0 to 18 can actually preempt this particular interrupt. Yes.
What happens when you set it to 4?
When you set it to 4, it means that only bits 0 to 4 are used for sub-priority, and bit 5 through 7 are used for the group.
Oh, so it actually doubles in size.
Yes. You have twice as many groups now, right? Because you got 1 more bit for the group here. But you have half as many sub-priorities per group.
Where is that correlation? How are you making the correlation between a 5 and the field layout and the 4?
5, bit 5.
Okay.
4, bit 4.
Okay.
3,
so
bit 3.
Reducing that group set
Yes.
expands the preemptive.
No, it just moves. It just tells you where do you have the boundary between group bits and priority bits. Right? So if it's set to 5, it means that you write a priority level for your interrupt. So for a certain interrupt source, you have 1 byte where you can tell what priority it is. So 38, that's your priority now. And in the NVIC, in a different register, you have configured how many bits are supposed to be sub-priority, how many bits will be the priority or the preemption priority. Okay? If it's set to 5, it means that the last 5 bits will be sub-priority. The top 2 bits are the preemption priority. If it's set to 4, it will 0 to 4 will be sub-priority, and 5 through 7 will be your preemption priority.
Okay, so where did you set that the last 3 bits are always 0s?
That's implementation specific. So chip vendors don't have to implement all 8 bits of priority. So in this particular case, this is the Cortex M3, where bit 0 through 2 are not implemented, so you cannot set them. That's where this comes from. Was that a confusion? Maybe? Okay. So in a chip vendor, you will get, like if you look at a certain, like for Cortex M3, for example, from Energy Micro or from ST Microelectronics, you have to go and look at the data sheet, and they will tell you how many bits of preemption, of how many bits of priority they have implemented. And if they choose not to implement all 8 priorities, they can leave some of the lower bits unimplemented. So they will always be 0 then. And that will tell you which priorities you can actually choose from.
So the lowest we can go over here is just group 3. We can't go any lower.
In this particular case, yes.
In group 3, we'll only have 2 sub-priorities, 0 and 1.
Yes.
But not so.
I'm not sure if you can go to 0. I think you can go to group 0 and then everything will be preemption.
On
Yeah.
the previous slide, you were talking about interrupts in terms of peripherals, but that one in that example was for an MCU, right? The one we're just looking at?
Wait, which?
That's for an MCU, right?
This?
Yeah.
I don't understand. What's your question?
Well, my question is, I thought you were talking about it in terms of peripherals and then in terms of the processor.
There are, okay, the reset interrupt is a interrupt that's always there on any Cortex M3.
Yes.
Okay? And then you cannot change, you cannot change the priority of the reset interrupt. That's that guy up here. That's this one here. Right? You can't change that one. You can't change the priority of the NMI. You can't change the one from the hard fault. They are predefined. But for any other interrupt source, be it from the bus system, for example, there's a bus handler, a bus reset vector, there, or if it's a peripheral, they will be programmable by you. But then a silicon manufacturer or somebody who gives you his Cortex M3 can decide and choose not to implement all 8 bits of priority, which will then limit you again. Is this clear? Yes.
So if they don't implement 8, are you restricted down to 6 or 5
Yes.
bits, but you can still do groups and stuff?
Yes. But you cannot choose them in, of course, the ones that are implemented on. Okay.
Here's the next question.
Yeah.
If they don't implement some bits, which doesn't matter, whether
It will always be the lower ones.
always the lower ones.
Always. That's defined by ARM. Like they tell the chip manufacturers, if they buy the IP from ARM, you don't have to implement all of them, but if you choose not to implement some, you have to leave them from the bottom. Like it's always the ones down at the bottom, which makes sense if you think about it, because else you cut away from the preemption up here and that would just leave a mess. So these down here will not be implemented. The top ones are always implemented. How many is up to the chip vendors. Yeah.
So what was the purpose of the sub-priority level again? They can't preempt each other.
They can preempt each other, but it will tell you the order at which they will be executed in case they're pending, which is something that we will talk about in a second. Yeah?
Is it possible that 2 interrupts are at the same priority?
Yes.
So what if they opposite?
Then this next decision level will be the interrupt number. So the higher number or the lower number it has, the first it will come, like the higher priority it has in that particular case. So if they have the same priority level, interrupt number, like in the vector table, like the higher ones, it goes from the top to the bottom. So yeah, it's the interrupt number, so it would be interrupt number 4 would have a higher priority in this case than interrupt number 5. So it would be executed first if it's pending, and then the second one. Yeah.
Same question. So if they're same priority, wouldn't that be decided by the sub-priority level? Like how many
I think he meant same priority with like here, if both of them have priority 30.
Well, you can have that.
Yeah, absolutely. At reset, everybody I think has priority 0. Everybody. They have the same priority. And so it's by the order of in the vector table that they will come.
So
Yes?
it's our responsibility in software to set all these peripherals up on initialization of the peripheral?
Correct. If you want to use it. Oftentimes you don't care that much. Oftentimes you're fine with, if they don't preempt each other, it will get rid of any issues with the stack that could happen, but sometimes you want somebody that has a higher priority. So you have to change it. Now I'm not sure if it starts at, if they all get initialized at the lowest priority or at the highest priority. Something I would have to look up in the data sheet. Yes?
There's like Libero, there's like a default for stuff. If you say I want to use like
Absolutely. There is a default. And if you go into the manual, that's the default. So there is a default also for the priorities. I just don't remember right now if it's the highest or the lowest. I know it's not a midpoint. It's one or the other. But I forgot which one it is.
Didn't you say there are 15 defined interrupts Cortex M3?
ARM defines 15 interrupts that have to be certain specific interrupts that happen. And then the rest are interrupts that implementation specific. They are per chip specific. So they are usually used for peripherals. Okay, so how do you use the priority? There's another little thing. So one of them is how they get preempted. But as I said last time, you can turn off all interrupts. And I made a little mistake here last time. If you use the prime mask, and if you write a 1 into it, it will turn off all interrupts. If you write a 0 in it, interrupts will be turned on again. But then you have another register which is called the base priority. With this one, you can turn off a certain amount of interrupts that are below a certain priority. So let's do an example here. We write in the priority register into R0. So let's assume this is pointing into the priority register of a certain interrupt. In this case, interrupt number 31. Then we write 61 into that. Oh, okay. We write 61 into R1. And then we store, there should be a 1 here, R1 into R0 offset 31. So that's the register that defines the priority of interrupt 31. And we say 60 into R0, and we write 60 into the base priority register. Did this now turn off interrupt 31 or not? So if you go back here, disable priority, write priority into base priority, right? So we write 60 in here. Write 60 into the base priority. Who thinks it will still be interrupting? Who thinks it will not interrupt anymore? More. Why do you think it's still interrupting? Yeah? But 31 is the interrupt number, right? That's why we write, this is offsetting from R0, 31. So R0 points to the base of all these base priorities, like the priority vector. So we write into offset 31 of R0 what we had here in R1, which was 61. So we set interrupt 31's priority to 61. And now we write 60 into the base priority. So are we ignoring interrupts 60 through 0 or 60 down? 60 down, right? The higher the priority, the less it is. So it's inverted. Okay, so this will turn off interrupt 31. Yes?
Top two lines of your code, can you only move in 16 bits from a constant at a time? Is there a way to do 32 bits?
Is there?
Other than those two lines?
How would you move a 32-bit number into a register if you only have 32 bits for an opcode? Right? That's the problem. What you can do sometimes is, with these crazy modifiers that Enoch was talking about, you can actually move more into a register by using shifts and immediates and stuff like that. So sometimes you can encode whatever you put in here with shifts, left shifts, right shifts, and stuff like that. So you can actually fill more than just the 16 bits. What? No. Yes? Yes.
He said that the below of certain priority means that
Priority number higher.
so when we
So
60,
it's confusing. Lower priority means a higher priority number. So it's going the other way around.
Yeah, but here it's I can't understand why it's turned off to 51.
Because we wrote 61 into the priority register of interrupt 31. So we set interrupt 30 to a priority of 61. And then into base priority, we write 60. So 61 is below the threshold of 60, so it will be turned off.
Another question. What is the difference between false mask and pre-mask? You mentioned
Yes. That was on the last slide. Prime mask is to turn off all interrupts except interrupt priorities -1, -2, and -3. If you write a 1 into fault mask, you will also turn off the hard fault. That's the only difference. Usually, you don't want to do this unless you really are sure that this is what you want to do. Because then all of a sudden you can do diffs by 0 and all kind of things, and it will just all be turned off. Sometimes that's also what you want to do, because sometimes you cannot guarantee an input, so you want to turn off the hard fault, because else you end up in the hard fault handler. So you can turn it off and do some dangerous code before you jump back.
Is this supposed to be the strd instruction store?
Yeah.
They're supposed to be R0
R1.
R1.
Yes. That should be R1.
Is that a store package?
Yes. Okay. All right, let's finish up with this big question of what exactly is an interrupt handler. So an interrupt handler is really just a glorified function. And where does the microcontroller find these functions? Well, they are defined in the interrupt vector. And the interrupt vector is stored at address 0, where the first one is the MSP, so that's the master stack pointer. And then they start coming down. So exception number 1 will be, the function pointer will be stored at address 4, 8, C, and it goes all the way down until the vector is filled. Yeah?
Will the handler also be responsible for making sure that the interrupt is cleared?
You're jumping ahead, we get there. How does this work? Well, on the case of the Cortex M3, they're all of the Smart Fusion, they're all defined in this file, startup A2FFXXS. There is a vector with the different pointers, and here, so these are labels into memory, and there is another file, and the link, and there is further down, you have the definition of all these different labels with the functions that they implement, and you then make sure that they get put to address 0 inside of the linker script. So in here we tell it this is a vector that we have here, and down here we tell the ISR vector should be put at the very, very top of the .text section, which starts at address 0. So that's how the link happens between these functions or memory labels and where they will be put, and making sure that they go into memory address 0. And the linker takes care of that for you. Interrupt handlers then are defined with a .global. So this is a function call, right? Reset handler. If you looked here before, we have the reset handler here defined. So over here, it's a global reset handler, and this is the implementation of the reset handler. So this is really the code where your microcontroller will start execution. It's not main, if you noticed. Like in C code, if you write int main, you expect that's where the code starts. No, that's not true. The code really starts executing in the reset handler. And I encourage you to go and find this file and look at the reset handler to see what it is doing. Because what it's doing, it's initializing memory. It's writing zeros into memory locations, into the BSS section. And then at the very end, it jumps to main, where it starts execution.
This was at AS.
This file here.
Yeah.
Mm-hmm. Yes? If you notice, I'm sorry, this should actually be inverted. I thought I did that on one of the slides, probably last week's slide. This is 1522, and then it goes here. So what this does is it says .global GPVN vector. It's section ISR vector. Right? These are assembly pre-instructions that will be used by the linker. So this will tell, this is the section called ISR vector. If you look down here, in the linker script, you can refer to this section now. So it will take this vector that's defined in here and put it at this location in the memory. And because there's nothing else really before that, this will be as address 0, or wherever it's supposed to be. the reset vector is not overwritable because you need that one. But all the other interrupt handlers are defined like this. They're a weak NMI handler, type, function, and then they're just infinite loops to it themselves. So a B dot means in assembly that jump to my memory location. So the dot is referred to the current memory location where we are at. So this will just be an infinite loop. It will just stuck there and wait for you to stop the system to see what happened. But you can overwrite them. And you can overwrite them, for example, in C later on by defining a interrupt handler with the keyword underscore attribute interrupt, void, and then you just have to choose the name that was defined over here in this interrupt handler vector. And that way you overwrite whatever they defined in this weak defined interrupt. So we'll overwrite these pointers using your functions. And now instead of going to that infinite loop in that predefined function, when interrupt happens, you will jump into your own interrupt handlers. And then inside the interrupt handlers, you have to do all your handling. So in this case, we disable the timer interrupt, we clear the timer interrupt. So we go to that RIS interrupt there and write a 1 into it to actually turn it off. And then we have to clear the pending interrupt in the NVIC to re-enable them later on. Okay? So now, what happens before an interrupt service routine gets called? It's kind of like a function, but not really, right? As we said last time, we have to take care that registers get saved. We have to make sure that the stack pointer stuff is okay, because we just jump from anywhere inside a code, start into a new function. So we have to take care of all of this. The nice part is the Cortex-M3 or the NVIC actually takes care of that. As soon as an interrupt appears, this is what's going to happen. It automatically saves the program counter, the status register, R0 through R3, R12, the stack pointer, and the link register. And it actually puts this automatically on your stack for you. Okay? Then, while it's busy doing that, because the stack is somewhere in memory, so it has to be transferred over in the memory, at the same time, it will fetch the exception vector. So it will go, see which interrupt happened, read the memory location, put that into, fetch that memory location, update the stack pointer to point to the new location because it just pushed a bunch of things onto the stack. It will then update the IPSR, which is the lowest few bits of the status register, with the current interrupt handler, or the interrupt that's just executing right now. It will then set the program counter to the right interrupt vector, so jumping basically to that code. And it will at last set the link register to exec return value. And we'll look at that value in a second. That's like a specific return value that has to happen. Okay? There's a couple of other things that happen in the NVIC, like status bits get set and stuff like that. But these are the main operations that happen. So in what order would you guys put these registers onto the stack? Does it matter? How about...
We want PC to come off first, right?
Yes. So we can be optimal here a little bit. First of all, if you look at this sequence, right? The stack pointer gets updated, but we also store the stack pointer. Same with the PC, right? What about the status? We also update the status something. So we can do stuff here in parallel. If we start writing certain things before others, we can at the same time do stuff concurrently. So if you look at a time scale, this is how we write it actually onto this, into memory. We first write the program counter, the PSR, then R0, R1, R2, R3, R12, and very last the link register. And they will be put into memory locations n-8, -4, -32, 28, 24, 20, 16, 12. So we first store the program counter so that we can update it as soon as the reset vector comes. Right? We then store the ISR so we can start updating that one too, so that by the time the last link register is actually written into memory, we are ready to execute. And we don't have to wait now to make sure and update the PC back here. So we can do this as soon as it's actually in memory. The ISR itself, the IPSR, this is this magic status register. It's actually 3 registers in one. We have the APSR, we talked about those. These are the status flags from the ALU, right, where you can do conditional executions on. And then the IPSR, which is the lower part down here, which will tell you which exception number is executed right now. So which interrupt is being processed right now. Any questions so far? So now we are ready to actually treat our interrupt handlers exactly like a function, right? Because we know that we can use R3, R0, R1, R2, and R3. We don't have to store them or anything. They are the scratch registers. All the other registers, if you want to touch them and use them, it's like a regular function. We have to push them onto the stack and revert them at the end in interrupt handlers. Yes?
Kind of confused about the address in -8, -4. I'm not seeing a pattern over there.
I have to look it up. Why? I was actually a little astonished. I thought it's actually starting all the way down, but it's not. But you could probably do this in a burst 8 transfer. And just start at this address, and then it will flip over. That's maybe why these bursts are actually there, to allow stuff like this. Any other questions? Okay. 3 ways of getting out of your interrupt service routines. As you notice, the LR has this like weird exec return value. And what you can do is you can either branch to the link register, which then will tell the microcontroller, oh, we are actually returning from an interrupt, and it will revert the functions that it did before in the inverse order, and it will jump back and execute again from where it left, right? Because it stored the PC onto the stack, and now it will put it back into the PC. Or you can pop the PC, that works too, or you can load that value exec number, so this value into the PC itself. But the most common one is just BXLR, and you will get out of the interrupt service routine. This is the most common one, but there are other possibilities. Okay, nested interrupts. Now we're finally there where priorities really start to matter. So there are 3 different methods that can happen. You can tail chain them. We can have late arrivals, or we can have preemption itself. Tail chaining is what happens when 2 interrupts happen that have the same priority. So what happens is the first interrupt comes, it starts to get serviced, the stack will be put onto, and the register will be put onto the stack. We have the interrupt service routine, and because a second interrupt happened in between, we will exit the first one and immediately service the next one without unstacking everything again. And only at the end, when we are done with the interrupt, we unstack and the main program executes. So this way you have a more efficient execution of interrupt handlers. Second, late arrivals. So if one interrupt happens and a higher priority one happens, while we are still stacking, it will actually execute the higher priority one. As long as this higher priority one happened before the vector fetch. Right? Because the vector fetch hasn't happened yet, so the higher priority now happened. It fetches the vector for the higher priority and will start executing that handler back here. Once it's done, it will tail chain the second one and actually execute the first one immediately after, without unstacking and restacking again. And then at the very end of both of them, it will unstack and we will back in the main program. Yes?
So it does finish stacking from the first interrupt?
It's the same thing, right? Because the stacking takes the main program and puts it onto the stack. There's nothing it has to go and fetch for the interrupt service routines, except the location. And as long as this vector fetch here hasn't happened yet, it will fetch the one of the higher priority. Vector fetch is when it goes into program memory and reads the jump location or the memory location of the interrupt service routine. So when it goes and reads, for example, address 8, And whatever is there, it will be loaded into the program counter to start executing the interrupt service routine. So as long as this fetch hasn't happened yet, it will execute the one of the higher priority. Yes?
I can't understand. What's the difference between before vector fetch and after one, after that?
After the vector fetch, then you fetched already the vector. You know where you're jumping to. So if this interrupt happens after vector fetch, we will have the next case, which is preemption. Because now you basically started executing the interrupt handler of the lower priority. Now, what will happen is, let me jump one further, is preemption. So in this case, what happens is a higher priority one comes in while the interrupt service routine of the lower priority is already running. So what has to happen is we have to take and stack everything from this interrupt service routine, go into a vector fetch, interrupt service routine of the higher priority one. Once we're done, we are jumping back into this guys, and then we are jumping back into the main program. Make sense? Right? Yes?
Does that cause any trouble when you are trying to exit the routine number 2? Like
Yes. And this is why we have this return value, like the exec return value. There are there are 3 different values that you can have. So the definition of it is if bits number 31 through 4 are all Fs, and then the last one is indicating how it should return. On the Cortex-M3, these are the 3 different values. So if it's a 1, it will return to handler mode. So basically we are now, we preempted somebody, we have to return to another handler mode before we can go into threat mode back. If it's a 9, it will return to threat mode using the main stack. If it's a D, we will return to the threat mode but with the process stack. So there's a little detail there. The stack pointer that we have, there are actually 2 shadowed stack pointers in the background, and you can switch between them by using these functions basically. So far we always have used the main stack because that's the easier one to use. But you have a process stack that you can use if you have applications. So you can give applications a separate stack that they can use, and they can be separately in a different memory location so that the main stack, where for example your kernel is running in, has its own stack and the applications can access it themselves. So with this particular application, you can tell with this return value, you can say, I want to jump back into an application, or I want to jump back into basically kernel mode itself. Most of the time, it will be F9 and F1 and not. And that's actually what happens here. So in threat mode, the link register will be set to FFFF9 because we are jumping back from this thread into main program. But then another one gets interrupted, so the link register will be set to FFFF1. So that back here, when we pop this link register back into the program counter, what will happen is we will return to handler mode, and only here, when we pop this link register, because that was on the stack, it got unstacked here, then we will jump back into threat mode itself. Any questions? Yes?
So if you don't use the VXLR command,
Yeah.
you pop the program counter, how does the microcontroller or the assembler know to do everything else because you've already popped one off and knows to pop everything but that one off? Or do you mess your stack up by using a different command?
Good question. I mean, if you pop the PC from the stack deliberately, I'm not sure how it's implemented in hardware. It's a good question. I do not know.
So if I were to use the pop command, do I have to worry about?
I don't think you have to worry about it, no. It will do the right thing with the stack and unstack it properly. It could be that it sees that you actually came from a pop instruction and not get that one from memory again, and then unstack the rest of it. That could be, yes.
But is he asking what preemption does?
No, it's, I think at least, let me see if I understand it right. Basically what he says is if you use one of these instructions, okay. No, you cannot do it. You cannot get it from the stack. What they say is if you, very often the link register will be pushed onto the stack. So when you enter an interrupt service routine, oftentimes you push that onto the stack because you will do other function calls just to save it. And so what you can do is, because it's now on the stack, at the end you can just pop it into the PC directly instead of back into the link register. But it's the same function. What will happen is the value of that link register will be written into the PC, and that's the sign of returning from an interrupt service routine. So it's the same thing as that happens in BXLR. As long as the LR has been untouched, what will happen is it will take the content of the link register, write it into the PC, and because it's the return exec value, it will know, okay, we're returning from an interrupt service routine.
So VXLR also pops that value off?
No. Think there are two different stackings and popping and stuff happening here. So the stacking and the unstacking, that happens automatically. That's always the same thing. And there, what gets saved is the program counter, right? So you can go back to where we were at. And it saves the link register because who knows, maybe we were in a function call somewhere, so the link register was actually the return value of somewhere else. So we have to save that one too. And then at the end, we will write into the link register this return exec value, okay? So if you get into a interrupt service routine, the link register will have this special purpose value. Now, you can either branch and exchange to LR, which it still has that value at the end, and you will write that back into PC and you will get out to where like the unstacking will happen. Or what sometimes happens is that people push the link register automatically just onto the stack.
Oh, so if you push it yourself,
yes,
then you can use the pop.
Yes.
Okay, I'm good then.
Okay.
I was just wondering how.
Yeah, no, I agree. I was confused too. If you push it in your interrupt service routine onto the stack, then instead of having to put it back onto the link register and then do a BXLR, you can just pop the PC. So you basically take that value from the stack right into the PC and don't have to do the branch and exchange later. Yes? No, that all happens automatically. Basically, as soon as the microcontroller sees this exec return value in the PC, it will know, okay, I have to unstack everything that I put onto the stack because I'm returning from an interrupt service routine. And during that unstacking procedure, what happens is that all these registers will get reset, and at the very end, it will pop the PC back out and write it into the PC, so it will continue where it was before. Yes?
I know, looking at, I have last Thursday's presentation here.
Mm-hmm.
Will you post the changes about the preemption?
Absolutely, yes.
Okay.
Yeah. All these slides, are after the lecture, I'm going to put them all online. Okay. So we talked about this sharing of interrupts. So we only have 240 different interrupt lines. Unfortunately, that's oftentimes not enough. And most of the times, every peripheral only gets one interrupt. So within the peripheral, you might have multiple things you want to tell the core. So you have to have a way of sharing interrupts. The very typical way of doing this is you just have a status register in your peripheral. And that way you can have a lot of different interrupts. Now it's your responsibility as software engineers, when you go into an interrupt service routine, you know from which peripheral the interrupt came, but you don't know what particular interrupt on that peripheral actually caused this particular interrupt. So what you do is you go and read a status register in your peripheral, and there you will have bits, ones and zeros, telling you what was the cause of this particular interrupt. So here's an example of the UART, which is the serial port on your microcontroller. It has the interrupt status register is at this particular location, and then it has bits number 3 through 0, which will be a certain number. And this number will identify what caused the interrupt. So, for example, the highest priority one, this is the receiver line status interrupt due to an overrun error. So you received 2 bytes in your receiver buffer without you having read the interrupt. So you had an overrun on the buffer. That's the highest priority one. Then this number can be a bunch of other different signals for different types of interrupts from your UART. Now you have the other problem too. You only have one interrupt service routine. But what if you have multiple C functions you want to execute for this particular interrupt service routine. And what if this has to be in a way dynamic, where you have a library, for example, a driver, right, that has the UART in there, and you want to tell the driver, hey, if you receive a UART interrupt, please call this particular function. And this is what function pointers can be used for and handlers. This is a very elegant way of how to register certain functions for a call of an interrupt. So in this particular case, we defined a function pointer handler. It's called radio alarm handler T. And during the initialization of this particular peripheral, so a radio, we register this handler. And what it will do is it will say the radio alarm fired is equal to this handler. So this function here will now point to the handler I gave into the init function. This can be a function pointer. And then when the interrupt happens, what you can do is at the very end, this is the way of calling a function pointer. This is hard-coded, but you could imagine that instead of having in this interrupt handler only one call down here, that this is, for example, a linked list. And now all of a sudden you can have as many functions registered to listen for a certain interrupt as you have in the linked list. Right? So this is more of like a C technique of how to deal and register functions. Functions don't have to be always called by their names. You can actually give people pointers to your functions, and this is a way of calling these particular functions later on. Okay, a couple of problems, very common pitfalls that can happen. If you have too many interrupts, so if you generate way too many interrupts, you can overrun your code, and you will just always be stuck in an interrupt handler, and you will never execute your main code anymore, right? If you just keep generating the same interrupt way too fast, and your interrupt handler didn't have time to execute an exit, it will just tail chain the next one and the next one and the next one. You're stuck in your interrupt handler. You can have concurrency issues, and that's actually a really, really big problem. Remember, interrupts can happen between any assembly instruction. And C instructions don't map to one assembly instruction, right? A C instruction can be a lot of different assembly instructions that have to be executed for it. So don't assume that within one C function, you can't be jumping into an interrupt service routine. This is very, very dangerous if you start modifying global variables. If your global variable is stored somewhere in memory, remember what happens if you add 1 to a global variable? Well, you first go load the value into a register, increment the register, and write it back. So what happens if we loaded the register, we go into interrupt service routine, the interrupt service routine now modifies that same memory location, we come back into the original code, and we now store that old value back into that global variable, right? You just completely ignore whatever the ISR did on this global variable because you wrote it right back. This is what's called concurrency. So if you are modifying specific dangerous global variables, what you have to do is you have to turn off interrupts, modify the global variable, turn interrupts back on. That's what this prime mask is used for. Yes?
So if you're masking interrupts, do they just sit in the pending state until you say, okay, I'm ready to
Yes,
go back to them?
exactly. They just wait for you until you re-enable them. Because then it looks in which are all pending, and it will start executing. You can also lose interrupts. Yes, so if you make a state machine, don't always assume an interrupt will come in. It can happen that you lose them. So sometimes they are just a glitch on the line and don't get asserted properly, or sometimes somebody else reads a register and clears an interrupt pending status. So for example, if you have an interrupt service routine and you have a bug and you actually overwrite the whole and clear the whole register out, everybody else's interrupts will be ignored and your state machine might deadlock itself. So you have to be aware of this possibility that interrupts don't always have to happen. Usually it shouldn't, but it can. Okay, quick summary. There is default interrupt handlers that are already registered, but they're defined as weak. You have to overwrite them if you want to actually hear these specific interrupts. Initialization, you have to enable interrupts at the NVIC and inside of the peripheral. And when an interrupt happens, what you have to do is you have to clear the interrupt peripheral. Sometimes happens automatically, but not always. You have to clear the pending bit, and yeah, potentially have to disable all interrupts temporarily if you want to modify global variables. Okay, any questions before we move on and rush through a couple of other things I want to tell you, guys? No? Okay. Quick one. Office hours today is only until 2:30, so 2 to 2:30 because I have a meeting at 2:30, but that's only today temporarily. Graduate student presentations, we talked about it last time. Demo a platform, come up with the platform and let me know. We have 19 grad students. This will be 5 lectures at 4 students each with 15 minutes per presentation, 15 minutes sharp. So I will call you and stop you. It would be good if you're a little bit short of that, so if students have questions, we can ask you about it. Please sign up on this link. I also posted it to the Canvas announcements. Propose your projects by February 21st. So send me an email, come to my office hours, and we can talk about what platforms you want to present, and has to happen by February 21st. Projects. There were a couple of questions already on what happens in projects. Well, the idea really is think big, right? Think about, I want to build a Segway, but then make it smaller and simpler, and build a little model like this one here, right? But think big, like have a good idea, have a great idea, and then figure out how you can make this smaller and easier. For example, this person here built an air guitar. So what he did is he made this instrument up here, which was basically a touch instrument for a guitar that was just registering when he was touching one of the little pads, and then he had a little accelerometer with which he was strumming itself, right? So it's a very, very cool idea. And last year we had other musical instruments that I showed you before. Somebody made a guitar, what are they called, pedal thingy that like distorts the sound and does all kinds of stuff. So musical instruments are a great way of doing stuff. This is a teeter-totter that was built. So this thing was basically keeping itself in balance with fans on here. So it was like keeping it approaching at level, while over here it had like a sensor looking at the height itself. So an interesting control system kind of problem where you have to deal with noise and motors and stuff like that. Fairly hard problem actually to deal if you don't do it properly. Think about robots, right? Lots of robots have embedded systems. These guys made a little Knight Rider that they drove with a Nintendo gamepad, and they had a little display on top that was driving around and telling you which direction you're going. These guys made a little game. They used Nintendo, I think they're N64 controllers, and they made a little game on a small little LCD display. Absolutely fine. You can go more sensor direction, so these guys made a radar. So they had a little display with the radar information, and then this guy up here was basically scanning of seeing like who is where and where do I get a reflection from. These are simpler things. Goal here is that you have sensors, that you have some motion, and that you have some code that you have to program it. I will have a whole handout that I will give to you guys with more instructions on how to select a good project. There will be some more researchy type projects that I will propose later. So for example, this person here tried to make a power monitor inside of a cube that's about that big. So you might, and that's wireless too. So he started prototyping it, he did a lot of different circuitry, and you can actually see the different phases on here that he got done during the class. He didn't finish all of it, and we didn't really expect him to finish. I think if we finished them, I'm not sure why he was in this class at all. But he got most of the parts done and most of the parts working, so now he's a grad student and this is his research project. So think about it this way. You can use and build a system that later on you want to use in grad school or for your research. Absolutely fine. Come and talk to me, and I will have a couple of others that I will propose. Another one, not entirely embedded systems developed, but that was your TA, An, actually made this one. The goal was to make 3D PCBs, that you have a 3D printer that puts down plastics, and then we put in ink into holes that it prints inside to make basically a cube that could light up LEDs or basically in 3D have electronics itself. They got so far as to print actual circuits onto 3D made substrates with ink that they developed themselves that actually worked. So the video here actually shows that this LED here blinks, and this is a silver ink that they used for conductivity. Another one that was what happened last year was this one here, a quadcopter. You can clearly see in here, you know this board, right? They made a quadcopter, so a quadcopter programmed by the Smart Fusion itself to fly around. And these particular students actually pushed this further in their computer engineering senior design as their final project. So if you are a computer engineer, you can absolutely start your senior design in this class, get something off, prove something that you want to do later on. Of course, for the senior design itself, you have to add something to it. So in this particular case, they made the frame and the basics for this class, and then for their senior design, they added a camera and I think a GPS to the whole system and make it more robust. A couple of ideas, starting points, last year's projects, you can find them at this link here. We have past year's University of Michigan 373, which this class is actually modeled after. Go and look at their projects. There are a lot of different ideas. You look at Cornell's embedded systems program that they have. They are more control-oriented, but they might give you some good ideas. The link is over here. And as I said, I will give you some research ideas later on in a couple of weeks. Form groups, group size 2 to 4 people. The bigger the group, you have advantages. You can make more complex systems, but I also expect more. So I expect from a group of 4 people a lot bigger project than from a group of 2 people. So you have the advantage of choosing big or small depending on what you want to do. Proposals are due March 5th. That's Tuesday in lecture. And then on Wednesday and Thursday following thereafter, we will have talks. So I will meet with you guys for like half an hour, talk about your project to see how you have to change your proposal before you can start with your final project itself. The proposal review that I will give you a booklet later on what I want in this proposal itself, but this can be, for example, a good proposal example where you have the goal, what's your statement, for example, this would be a sound meter, what do you have to do for this particular sound meter? I want a functional description telling me what this all does, how you plan to implement it, what functions should be done where, what are the different entities that you have to get. I want a functional diagram that tells me and basically puts what you have in here into a diagram. So for example, we have an audio microphone amplifier, anti-aliasing filter, a keypad. Here we would have our Smart Fusion user interface, ADC, sampling everything, and then some output over here. All right? So please write down on a little paper what sticks of the interrupts, what was unclear, and I should go over again